So let's talk about multi-core caching. So here's our abstract version of caching. Our abstract version of the locking. So let's look. Our abstract version of locking is we have some CPUs. And this is 0. So what it looks like is we have each of our CPUs, they're connected to a bus, they go to memory. And when we do a lock, we will use some sort of a atomic primitive. So we might use, for instance, exchange. And the idea is that we will go ahead for a given CPU that does an exchange, and it'll go ahead, it will read from the bus the existing value at that address, and then write to the bus the new value. And it will do that, locking the bus between those two different operations so that nothing else can happen along the way. Okay. That is the abstract version. The problem with that, and the way in which that's not really true, is the fact that access to memory is expensive. Right? It's on the order of 100 nanoseconds. And since we're doing instructions at about 1 nanosecond, that takes about 100 instructions to do, so that's quite expensive. So we're going to go ahead and update this picture to closer reflect reality. Right? We're going to basically add a cache here. And we have some requirements that we have for our cache. So one requirement we have is cache consistency, right? And cache consistency just means the order of reads and writes that we happen between memory locations is maintained. And then also we have cache coherence. And that basically means that when we are reading or writing a single memory location across multiple CPUs, they all have to agree in some way. So what we're going to do here is we're going to actually add a cache to each of these. And that more closely reflects reality. This is closer to actual. And so somehow we need to take account of the fact that if I've got a value cached on CPU 0, there's a couple possibilities. What if CPU 0 wrote to a value and that's now in the cache? Well, if CPU 1, 2, or 3 tries to read that value, it better get the updated version. Or similarly, what if CPU 0 had a read that it did and kept that in the cache, and now CPU 1, 2, or 3 actually writes that value? That should invalidate the cache in some way. So we're going to look at some protocols for dealing with caches. There are a lot of different ways you can do things. I'm going to present kind of a vanilla approach of how this works. So the first thing we're going to do is we're going to divide the cache into fixed size chunks. We're not going to be storing bytes. We're not going to be storing words. Instead, we're going to be storing 64 bytes of contiguous data, which we're going to call a cache line. So we're going to, so these are each 64 bytes, and those are all 64 byte aligned. So when I go read a value from memory, let's say in CPU 0, I'm not going to just read a single byte. I'm not going to just read 32 bits or 4 bytes. I'm going to go ahead and read all 64 bytes and fill up this cache line. Okay, so the cache is composed of cache lines. And what I'm going to say is that each cache line in this cache is in one of 3 different states. So our 3 states are modified and shared or invalid. We also are going to define some messages that are sent between CPUs. Okay? And so these are going to be 3 messages. So one is going to be invalidate, and this deletes from the cache. The second is going to be find, and this specifies, so basically, does any core have a copy? And I said 3. This is actually all we have are these 2. So invalidate and find. So I, as a core, can request that all the other cores invalidate what's there, or I can also request that all the cores figure out whether they have such an address. Okay, and what they're going to do if they do the find is, we're going to talk about in a little bit. All of these messages are broadcast. That is, they go to all CPUs. This is the simplified version of a cache protocol. There are certainly more advanced versions of cache protocols, for instance, where we have information about where things are cached. Or maybe what we have is each CPU is responsible for a range of addresses. And so if you're interested in that address, you talk to the CPU who's responsible for it, and then that CPU knows which other CPUs actually have particular portions of that space currently in their cache. So it saves a little bit of broadcasting to everyone. But for now, we're going to just use this simplified version, which has been used in the past for sure. Okay, so what's going to happen? We have basically a state machine. So let's look at that state machine. It can be one of three states. Let's look at what happens. So if we get an invalidate and we're in this state, we're not going to do anything. Okay, right? So if we get this message and that cache line is already in the invalid state, then we're not going to do anything. So the CPU does a write of the entire cache line. Okay? Then what's going to happen is we are going to go ahead and go to the modified state. Modified state says basically we have a more updated version than anyone else does. As well, what we're going to do is we're going to send invalidate, right? So that's going to just say to all other CPUs, your cache line is no longer valid. Now there's some work that we have to do if we're writing to only part of the cache line, but let's just assume we're writing to the entire cache line. Okay, so we have now the latest version and we have invalidated everyone else's. Let's say we do a read. Okay, so I'm sorry, so this is we send invalidate and this is on CPU write. If we do a CPU read, right, and here all of the cache line is going to read the entire cache line, then we're going to go ahead and go to the shared state. However, it's important to realize that there may be some other CPU that has a newer version, that has a modified version of this particular cache line. And so therefore, we need to go ahead and do a find. So we're going to do a find. Find says to the other CPUs, if you have this cache line modified, then go ahead and write it out. So we're going to do a find. We're going to go ahead and read from main memory, and then go into the shared state. So this is everything that can really happen in the invalid state. We receive an invalid, I suppose the other thing we should say, if we get a find, we're going to also just do nothing. Find and invalidate, both do nothing. So no ops to keep us in the I state. Otherwise, we might go to the shared state if we read a copy, or in the modified state if we write. And for the read, we've got to do a find first. So this sends the find. All right, what do we do next? Well, let's say we're in the shared state. Okay, if we have a find, we don't have to do anything. Why do we not have to do anything? Because we don't have a modified version. We have the same version, or the same copy that, as far as we know, is in memory. Okay, and actually, we do have the same value that's in memory, because if some other CPU had a modified version, we don't have a shared version, because the rule is we can have multiple shareds are okay, but only one M, only one modified, with no concurrent S's, no concurrent shareds, because they would disagree about the value. Right, so what happens in this state? Again, let's say on a write, right? So if we write the entire cache line, we're going to do the same thing when we're in an invalid state. So on CPU write, we are going to send invalidate. Okay, we don't bother updating the memory. So what we have is a write back cache. So a write through cache says whenever you write to the cache, you also write to the underlying storage. Here we don't. We only write as necessary, in particular when we get a find. All right, so what do we do on the find? We do nothing. On an invalidate, so on an invalidate, we do nothing. On a find, we do nothing. On an invalidate, on a find, we do nothing. On a write, we do this. What do we do on a read? Well, on a read, we don't have to do anything because we've already got it in our cache. That's one of the cool things about caching, is if it's in our cache and we read it, it's very, very fast, right? We can run at full speed for our instructions. Okay, and then finally, what if we're in the modified state? Well, on a read, we could just go ahead and read what's in the cache. On an invalidate, then we are just going to go ahead and set it to invalid. How is it that we could have written a value, we never wrote it out to memory, and yet now we're asked to invalidate? If some other CPU overwrote that same cache line. So we made some changes to the cache line, and then they go ahead and make some changes to the entire cache line as well that completely overwrite ours. So therefore, we'll just throw ours away. On a write, right, this is a CPU write, a CPU read, we again do nothing in the sense that we do write to the cache line, but we don't change our state. We're still modified. And then finally, on our find, so on a find, our job is write cached value to main memory. We go ahead and write the cache line to main memory. So remember that something that was in invalid state on a read sends a find and then reads from main memory. The sending a find, we actually respond to on the find and write the cache line to main memory before the read happens. So there's some synchronization that's happening here on the find in the sense that you send the find out all the CPUs and you either wait to be notified that it's okay, right? So that someone has actually, either no one needs to write to main memory or someone has done the write to main memory before you read from main memory. So the cost of that, of course, would be 2 memory cycles. So we'd have 100 nanoseconds to write to main memory and then 100 more nanoseconds to read from main memory. So that is our state diagram. Our invariants, right? Let's just look and see. Right, so this is for a given cache line. Can we have 2 cache lines that are both in the I state? And the answer is yes, of course you can do that. Okay, you can have, this is on one CPU, on another CPU. So can you have invalid and invalid? Yes. Invalid and shared? Yes. It's also invalid and shared. Can you have invalid and modified? Yes. So one CPU's just never tried to, let's say, read a cache line, another CPU modifies it. That's certainly fine. Modified. Can we have shared and shared? Yes. Can we have modified and modified? No. Modified and shared? No. Modified and shared? No. So one modify across all the CPUs, and that modify can't have any other shares. So it's one modify and all the others invalid. But what that does mean is if that CPU is just sitting there and reading and writing that particular cache line, it's very, very fast, right? There's no bus traffic to the memory bus. There's no waiting. These are approximately 100 nanoseconds for the memory. We're just reading, writing, reading, writing, reading, writing, nanosecond, 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 assuming we can go at full instruction speed for the cache. So what that means so that deals with the one core that's repeatedly reading and or writing, is we just get exclusive access and they happen at full speed. And there's no communication that's needed, right? We don't need to communicate to any other cores. If you've got multiple cores in the shared state, then they can be doing reads all day long, again, completely quickly. It's only when a write happens from a core that's not in the modified state that we have to have, a read or a write happens, that we have to have any sort of communication, right? A read means we've got to send a find, and a write means we're going to go ahead and send an invalidate. So there are more complex state machines. So for instance, some state machines add an E for exclusive, all right? You can have more complex interconnections. So we really don't normally have just a bus across all CPUs. We might have, for instance, within a particular die, that is within a particular piece of silicon, you might have a little on-chip network. And then for multiple CPUs across multiple chips, you might have some sort of an off-chip network. And as I mentioned, we also have cache directories. So cache directories somehow keep track of which CPUs have which copies of data and also their state. So this protocol ensures that every core reads fresh data. We still have deals with things like, we have to deal with things like on a CPU, if we have got several non-atomic operations where, let's say, read and address, and then we modify the value based on what was there, then that's a situation where we've got a critical section, right? Where it's read, do some computation, write. There, we've got to deal with locks. Or if we have a data structure that requires several instructions to move from one invariant state to another invariant state, again, we deal with locks. But as we're dealing with locks now, we are going to keep in mind that we know about these cache situations. So what we've seen is the exchange instruction used in JOS and XV6. So that is one atomic operation. There are other atomic operations as well. So for instance, test and set, or compare and swap. Now, how does this work? Something like the exchange actually does a read and then has to do a write. So how does that actually get implemented? Well, what will happen is the CPU gets the associated cache line in a modified state. Once it's in a modified state, it then goes ahead and does the operations that it needs to do, the read and the write. What's important to understand is that it defers any find until the operation is done. So you can imagine we're in an invalid state. We do an exchange. The CPU switches to a modified state, read the value from memory, and then go ahead and write to the cache so that the cached value now has the modified value and it can return the correct value for the result of the exchange. If a find happens in the middle of that, it ignores it and waits till it has actually finished the write.